In the year 1929, Edwin Hubble made an observation that shattered our cosmic arrogance forever. The universe wasn't just bigger than we thought. It was expanding, racing away from itself at speeds that defied comprehension. That discovery birthed modern cosmology, the science of everything that exists. For nearly a century, we've built our understanding on that foundation. We've mapped billions of galaxies, detected the afterglow of the Big Bang itself, weighed galaxy clusters with the gravity of Einstein's equations. We even discovered that mysterious dark forces dominate the cosmos, dark matter holding galaxies together, dark energy tearing them apart. Our best model is called the Lambda Cold Dark Matter Model. With just 6 parameters and 1 equation, it claims to explain the entire universe. But the universe keeps whispering secrets we can't quite hear. Right now, as you listen to these words, space-time itself is vibrating. Massive gravitational waves, larger than solar systems, are washing over Earth every few years. We've detected them, but their source remains maddeningly ambiguous. Are they echoes from the dawn of time? Collisions of supermassive black holes? Or something we haven't even imagined? Meanwhile, 2 separate teams of astronomers are locked in a cosmic dispute that threatens to break physics itself. When they measure how fast the universe is expanding today, they get different answers. Not slightly different, impossibly different. It's as if the universe is expanding at 2 speeds simultaneously. One team uses the cosmic microwave background, the baby picture of the universe. Another uses supernovae, the death screams of stars. Both methods are rigorous. Both have been refined for decades. Both should give the same answer. They don't. Then there's the case of the missing matter. Not dark matter, regular matter. The stuff that makes stars, planets, and people. Half of it is simply gone. We know it exists. The Big Bang's mathematics demands it. The cosmic microwave background confirms it. But when we count every star, every gas cloud, every atom we can detect, we come up short by billions of galaxies worth. It's the greatest heist in cosmic history, and we don't even know where to look for the stolen goods. And in the darkest corners of space, in the hearts of galaxies, something strange is happening to dark matter itself. It's not behaving like we predicted. In some galaxies, it seems to ripple like water, form standing waves, act less like a particle and more like a cosmic ghost, defying the very nature we assign to it. If dark matter can act like a wave, what else have we gotten wrong about the invisible scaffolding that holds the universe together? 4 mysteries. 4 cracks in our cosmic confidence. Each one could be a measurement error, a miscalculation, a misunderstanding. Or each one could be a thread that, when pulled, unravels everything we thought we knew about the universe. These aren't just puzzles for physicists. These are clues to the fundamental nature of reality itself. And solving them might require us to reimagine not just space and time, but our very place within them. Welcome to the edge of knowledge. Welcome to the mysteries that keep cosmologists awake at night. The universe is speaking, but to understand its language, we need a translator. That translator has a name that sounds like a secret code: lambda cold dark matter. Think of it as the Rosetta Stone of cosmology, the key that unlocked our ability to read the cosmic story written across billions of light years of space and time. Picture yourself as a detective, arriving at the strangest crime scene imaginable. The evidence is scattered across 14 billion years and 93 billion light years of observable universe. Your witnesses are ancient photons that have been traveling since before the Earth existed. Your forensic tools are telescopes that can see infrared whispers from the first galaxies and radio arrays that detect gravitational ripples in space-time itself. And the mystery you are trying to solve? Nothing less than how everything came to be. Lambda cold dark matter emerged from decades of cosmic detective work, piece by painstaking piece. It started with a bang, literally. Not an explosion in space like a firecracker on the 4th of July, but an explosion of space itself. Imagine the entire universe, every galaxy you see in the night sky, every star that has ever shone, every atom in your body, all compressed into a point smaller than the period at the end of this sentence. Then, 13.8 billion years ago, that point began to expand. In the first trillionth of a trillionth of a trillionth of a second, something extraordinary happened. The universe underwent a period of exponential expansion called inflation, growing from subatomic scales to the size of a grapefruit faster than light itself could traverse the distance. This was not a violation of Einstein's speed limit, because space itself was expanding, carrying everything within it like raisins in rising bread dough. As the universe expanded, it cooled. The unimaginable heat of creation began to dissipate, and as it did, the cosmos underwent a series of phase transitions, like steam condensing to water and then freezing to ice, but with the fundamental forces and particles of nature. First, the strong nuclear force separated from the electroweak force. Then, electromagnetism split from the weak nuclear force. Quarks condensed from pure energy, then combined into protons and neutrons. All of this happened in the first second. For the next 380,000 years, the universe was a glowing plasma, a cosmic soup so hot that atoms could not form. Light bounced endlessly between charged particles, like a ball in a pinball machine. Then came the moment of cosmic clarity. The universe cooled enough for electrons to settle into orbits around nuclei, forming the first atoms. Suddenly, light could travel freely. The universe became transparent, and that first released light still reaches us today, stretched by cosmic expansion into microwave radiation that fills all of space. This cosmic microwave background is like a baby photo of the universe, and lambda cold dark matter predicts exactly what that photo should look like. The model tells us there should be tiny temperature variations, regions slightly hotter or cooler by just 30 millionths of a degree. These seemingly insignificant ripples were the seeds of everything we see today. Gravity amplified them over billions of years, pulling matter into the denser regions to form the first stars and galaxies. But here is where our cosmic detective story takes a dark turn. When scientists calculated how much ordinary matter would be needed to create the structures we observe today, The massive galaxy clusters connected by filaments of gas, stretching across hundreds of millions of light years, they discovered something shocking. There was not nearly enough visible matter. Not even close. Imagine trying to bake a cake and discovering that 5/6 of your ingredients are invisible. That is the situation cosmologists faced. The solution? Dark matter, the invisible scaffolding of the universe. This mysterious substance outweighs ordinary matter by a factor of 5 to 1. It does not emit light. It does not absorb light. It does not reflect light. The only way we know it exists is through its gravitational pull. Galaxies rotate too fast to be held together by their visible matter alone. Galaxy clusters bend light from more distant objects far more than their visible mass could account for. The pattern of temperature fluctuations in the cosmic microwave background requires dark matter to match observations. Every piece of evidence points to the same conclusion. Most of the matter in the universe is invisible to us. The cold and cold dark matter refers to the speed of these mysterious particles. They move slowly compared to light, allowing them to clump together under gravity's influence. This clumping created the cosmic web we see today, with dark matter forming invisible halos that attracted ordinary matter like cosmic flypaper, seeding the formation of galaxies. But the universe had one more surprise in store. In the late 1990s, astronomers studying distant supernova, stellar explosions that serve as cosmic distance markers, expected to find that the expansion of the universe was slowing down. Gravity, after all, pulls things together. What they found instead defied all expectations. The expansion was accelerating. Enter lambda, representing dark energy, the most mysterious component of lambda cold dark matter. This is not a force in the conventional sense, but rather an intrinsic property of space itself. Empty space is not empty. It seethes with energy, and as the universe expands, creating more space, it creates more dark energy. This self-reinforcing cycle drives galaxies apart at an ever-increasing rate. Dark energy now dominates the universe, making up 68% of everything that exists. Dark matter accounts for 27%. Everything else, every star you see, every planet, every atom of every element forged in the hearts of dying stars makes up just 5%. We are cosmic minorities in our own universe. Lambda cold dark matter brings these components together into a mathematical framework of stunning precision. It predicts the universe is geometrically flat, that parallel lines remain parallel even across cosmic distances. It explains why the universe looks roughly the same in all directions. It accounts for the abundance of hydrogen and helium created in the Big Bang. It successfully predicted the acoustic peaks in the cosmic microwave background before they were measured. Yet this triumph of human intellect, this standard model that explains so much with so few parameters, is showing cracks. Those four mysteries we introduced, those signals from the darkness, are telling us that lambda cold dark matter, magnificent as it is not the final answer. The cosmic hum detected by pulsar timing arrays suggests gravitational waves from the early universe that the model did not predict. cosmic hum detected by pulsar timing arrays suggests gravitational waves from the early universe that the model did not predict. This discovery, announced in 2023, marks the beginning of our journey into the four mysteries that may force us to rewrite the cosmic story. Imagine standing in a perfectly silent room when suddenly you hear the faintest possible sound, a low-frequency vibration that seems to come from everywhere and nowhere at once. Now, imagine that this sound has been traveling for billions of years, not through air, but through the fabric of space-time itself. This is what astronomers have discovered, a cosmic hum pervading the entire universe, detected not with microphones, but with some of the most precise natural clocks in existence. Pulsars are the lighthouses of the cosmos. When massive stars exhaust their nuclear fuel, they collapse catastrophically, their cores compressed into spheres of matter so dense that a teaspoon would weigh as much as Mount Everest. These neutron stars, just 20 kilometers across, spin hundreds of times per second, sweeping beams of radiation through space like cosmic searchlights. Every time that beam crosses Earth, we detect a pulse of radio waves with timing more precise than atomic clocks. For decades, astronomers have monitored these cosmic metronomes, tracking the arrival times of their pulses down to nanosecond precision. They noticed something extraordinary. The pulses from multiple pulsars scattered across the sky were arriving slightly early or slightly late in a coordinated pattern. It was as if all of space was gently stretching and squeezing, changing the distance the pulses had to travel. This discovery represents the first detection of the gravitational wave background, a cosmic symphony of space-time ripples that fills the universe. Unlike the gravitational waves detected by LIGO and Virgo, which come from individual catastrophic events like colliding black holes, this background hum is the combined effect of countless sources throughout cosmic history. To understand how remarkable this detection is, consider the scale of the distortion. As these gravitational waves pass through Earth, they change the distance to a pulsar thousands of light years away by less than the width of a human hair. Yet by monitoring dozens of pulsars for over a decade, astronomers have teased out this infinitesimal signal from the noise. The technique is called a pulsar timing array, and it transforms the entire galaxy into a gravitational wave detector. By comparing the arrival times of pulses from pulsars in different directions, scientists can identify the characteristic pattern of gravitational waves. When a wave passes through, it stretches space in one direction while compressing it perpendicular to that direction. Pulsars in the stretched direction will have their pulses delayed, while those in the compressed direction will arrive early. What makes this discovery so profound is not just the technical achievement, but what the signal tells us about the universe. The frequency of these waves, with periods of years to decades, points to sources far more massive than anything LIGO can detect. The leading explanation involves supermassive black hole binaries, pairs of black holes, millions or billions of times the mass of our Sun, spiraling toward each other at the centers of merging galaxies. When galaxies collide, a process that takes hundreds of millions of years, their central black holes eventually find each other. They begin a gravitational dance, orbiting their common center of mass while losing energy to gravitational waves. As they spiral inward, they generate waves with wavelengths measured in light years, precisely the kind that pulsar timing arrays can detect. But here is where our mystery deepens. The strength of the signal detected by pulsar timing arrays is stronger than most models predicted. Either there are more supermassive black hole binaries in the universe than we thought, or they are merging more efficiently than our theories suggest, or something else entirely is contributing to the cosmic hum. This unexpected strength has opened the door to more exotic possibilities. Some theorists propose that the gravitational wave background might include contributions from cosmic strings, hypothetical one-dimensional defects in space-time left over from phase transitions in the early universe. Imagine cracks in ice forming as water freezes, but instead of ice, we are talking about the fundamental structure of space itself. These cosmic strings, if they exist, would be thinner than an atomic nucleus, but could stretch across the observable universe. They would carry enormous tension, containing the mass energy of a mountain range in every centimeter. As they vibrate and interact, crossing through each other or forming loops that collapse, they would generate gravitational waves at precisely the frequencies pulsar timing arrays observe. The implications extend even further. Some models suggest the gravitational wave background could contain echoes from the inflationary epoch, the period of exponential expansion in the universe's first fraction of a second. Quantum fluctuations during inflation would have been stretched to cosmic scales, creating primordial gravitational waves that have been reverberating through the universe ever since. There is another intriguing possibility. The signal might include contributions from primordial black holes, hypothetical black holes formed not from collapsing stars, but from extreme density fluctuations in the early universe. If these exist in sufficient numbers, their mergers throughout cosmic history would add to the gravitational wave background. What makes this mystery particularly compelling is that we are just beginning to explore this new window on the universe. The current detection represents only the tip of the iceberg. As pulsar timing arrays continue to collect data, improving their sensitivity with each passing year, they will begin to resolve individual sources within the background hum. Future observations will distinguish between different source populations by examining the frequency spectrum of the waves. Supermassive black hole binaries produce a characteristic spectrum different from cosmic strings or primordial sources. The polarization of the waves, the pattern of how space stretches and squeezes, provides another diagnostic tool. Even the statistical properties of the signal, whether it appears smooth or lumpy across the sky, offer clues to its origin. The European Pulsar Timing Array, the North American Nanohertz Observatory for Gravitational Waves, the Parkes Pulsar Timing Array in Australia, and the Indian Pulsar Timing Array are all part of the International Pulsar Timing Array collaboration. Together, they monitor over 100 millisecond pulsars, building an ever more sensitive gravitational wave detector spanning the galaxy. This cosmic hum represents more than just another confirmation of Einstein's general relativity. It provides a completely new probe of the universe's history and contents. The waves carry information about their sources that electromagnetic radiation cannot provide. They pass through matter unimpeded, bringing us signals from regions obscured by gas and dust. They encode the dynamics of the most extreme gravitational environments in the universe. Consider what this means for our understanding of galaxy evolution. Every major galaxy appears to harbor a supermassive black hole at its center, monsters containing millions to billions of solar masses. How these black holes formed and grew to such enormous sizes remains one of astronomy's great puzzles. The gravitational wave background provides direct evidence of these black holes merging, a crucial piece of the puzzle. The detection also raises profound questions about the early universe. If cosmic strings contribute to the signal, they would be relics from symmetry breaking phase transitions when the fundamental forces separated. Their properties would tell us about physics at energy scales far beyond what any particle accelerator could achieve, potentially revealing new physics beyond the standard model. The cosmic hum might even contain surprises we have not imagined. Just as the discovery of the cosmic microwave background revolutionized cosmology, providing a baby picture of the universe, the gravitational wave background offers a different kind of fossil record, one written in the vibrations of space-time itself. As we refine our measurements, we are building a new kind of astronomy. We must solve a fundamental question. What exactly is creating these gravitational waves? The debate centers on two radically different possibilities, each with profound implications for our understanding of the universe. Picture two scenarios. In one, pairs of supermassive black holes, each millions or billions of times the mass of our Sun, spiral toward each other in a cosmic death dance. In the other, impossibly thin cracks in the fabric of space-time itself, remnants from the universe's birth, vibrate and collide, sending ripples through reality. Both could produce the gravitational wave background we observe, but they would leave different fingerprints in the data. The distinction matters enormously. If supermassive black hole binaries dominate the signal, we are witnessing the final stage of galaxy mergers throughout cosmic history. If cosmic strings contribute significantly, we have discovered relics from the universe's first moments, fossils from an era when the cosmos was hotter than any particle accelerator could recreate. Let us start with supermassive black hole binaries. When two galaxies merge, their central black holes do not immediately collide. Instead, they sink toward the center of the newly formed galaxy through a process called dynamical friction. Stars and gas clouds that pass near the black holes get gravitationally scattered, transferring energy and angular momentum away from the black holes, causing them to spiral inward. Eventually, the two black holes form a binary system, orbiting each other at distances of a few light years. At this stage, they face what astronomers call the final parsec problem. The black holes have cleared out most of the stars and gas from their immediate vicinity, removing the dynamical friction that brought them together. Without something to extract their orbital energy, they could remain locked in this dance for longer than the age of the universe. This is where gravitational waves become crucial. As the black holes orbit each other, they create ripples in space-time that carry away energy and angular momentum. The binary slowly tightens, with the orbital period decreasing from centuries to years to months. The gravitational waves grow stronger and higher in frequency until finally, in a catastrophic merger, the two black holes become one. The gravitational waves from this spiral have a very specific character. Their frequency increases steadily over time, following a precise mathematical relationship called a chirp. The amplitude of the waves depends on the masses of the black holes, their distance from Earth, and the orientation of their orbit. Critically, each binary produces waves at a single frequency at any given time, though that frequency changes as the orbit decays. Now, consider cosmic strings. These hypothetical objects would be fundamentally different from anything we have observed. They would be topological defects, places where the vacuum of space got stuck in different configurations as the universe cooled. Imagine water freezing into ice so quickly that different regions crystallize with different orientations. Where these regions meet, you get grain boundaries, defects in the crystal structure. Cosmic strings would be similar defects, but in the fundamental fields that define the properties of space itself. A cosmic string would be unimaginably thin, perhaps only 10 to the negative 35 meters across, smaller than the Planck length where our current understanding of physics breaks down. Yet they would contain enormous energy, with each meter potentially having the mass of Mount Everest or more. They would stretch across vast cosmic distances, possibly spanning the entire observable universe. These strings would not sit still. They would vibrate at nearly the speed of light, whipping through space in complex patterns. When two strings intersect, they could exchange partners, like two jump ropes crossing and reconnecting in a different configuration. These reconnection events would create loops of string that would oscillate and eventually decay, primarily through gravitational wave emission. The gravitational waves from cosmic strings would have distinctly different properties from those of black hole binaries. Instead of a smooth chirp from a single source, strings would produce a cacophony of signals. Loops of different sizes would emit at different frequencies, creating a broad spectrum of gravitational waves. The amplitude and frequency content would depend on the tension of the strings and how they were distributed throughout cosmic history. Here is where observational tests become crucial. The spectrum of the gravitational wave background, how its strength varies with frequency, provides our first clue. Supermassive black hole binaries should produce a characteristic power law spectrum, with the amplitude decreasing at higher frequencies in a predictable way. The exact slope of this decrease depends on the distribution of black hole masses and how efficiently they merge. Cosmic strings would produce a different spectrum. The gravitational waves from string loops would peak at frequencies related to the loop size, with smaller loops emitting at higher frequencies. The overall spectrum would be flatter than that from black hole binaries, potentially even increasing at certain frequencies where particular loop sizes dominate. Current pulsar timing array data shows a spectrum roughly consistent with supermassive black hole binaries, but the uncertainties are still large. As we collect more data and improve our analysis techniques, we will measure the spectrum more precisely, potentially revealing deviations that point to additional sources. The statistical properties of the signal provide another test. Supermassive black hole binaries should produce a relatively smooth background, the combined effect of many sources at different distances and orientations. However, a few nearby or particularly massive binaries might stand out above the background, creating hotspots on the sky. Cosmic strings would create a more intermittent signal. String loops would produce bursts of gravitational waves as they oscillate and decay. Cusps and kinks on the strings, places where the string velocity approaches the speed of light, would generate particularly strong bursts. The background would be lumpier, with more variation across the sky and over time. Pulsar timing arrays are beginning to search for this anisotropy, looking for regions of the sky where the gravitational wave signal is stronger. Early results suggest a relatively uniform background, favoring the black hole binary scenario. But again, more data is needed for definitive conclusions. The polarization of gravitational waves offers yet another diagnostic. Like light waves, gravitational waves can be polarized, meaning they have a preferred direction of oscillation. General relativity predicts that gravitational waves should have two polarization states, called plus and cross polarizations. Alternative theories of gravity might allow additional polarization modes. Black hole binaries in general relativity would produce a specific mix of polarizations determined by their orbital orientations. Cosmic strings could produce different polarization patterns, especially if they involve physics beyond general relativity. As pulsar timing arrays improve their sensitivity, they will be able to measure the polarization of the background, providing a crucial test. Perhaps the most definitive test will come from detecting individual sources within the background. If supermassive black hole binaries dominate, we should eventually resolve the closest and most massive systems as distinct sources rising above the background hum. These would appear as continuous gravitational wave signals with slowly increasing frequency as the binaries in spiral. Several candidate binary systems have already been identified through electromagnetic observations. The galaxy OJ-287 appears to host two supermassive black holes with a 12-year orbit. ENG C6240 contains two black holes about 1,000 light-years apart. If these systems are emitting gravitational waves at the predicted levels, next-generation pulsar timing arrays should detect them directly. Cosmic strings would produce a different signature. We might detect individual bursts from nearby string cusps or kinks, sharp spikes in the gravitational wave signal lasting minutes to hours. Or we might see the continuous emission from a particularly large loop of string, distinguishable from a black hole binary by its more complex frequency structure. Multi-messenger astronomy provides additional constraints. If the gravitational wave background comes from supermassive black hole binaries, we should see corresponding electromagnetic signals. As the black holes merge, they interact with surrounding gas, potentially producing bright flares visible across the electromagnetic spectrum. Several groups are searching for these electromagnetic counterparts, though none have been definitively identified yet. Cosmic strings might also produce electromagnetic signals, though of a very different nature. As strings move through cosmic magnetic fields, they could generate electromagnetic radiation. Cusps and kinks might produce bursts of high-energy particles. Some models predict that cosmic strings could lens light from distant galaxies in a characteristic way, creating pairs of identical images. The implications extend beyond identifying the source. If cosmic strings exist, they would confirm that the universe underwent phase transitions in its early moments, potentially associated with grand unification of forces or other new physics. The properties of the strings would tell us about the energy scale of these transitions, probing physics far beyond what terrestrial experiments can reach. If supermassive black hole binaries dominate but their signal is stronger than expected, it might indicate that our models of galaxy mergers need revision. Perhaps black holes merge more efficiently than we thought, or there are more massive black holes in the early universe than current theories predict. Future gravitational wave detectors will dramatically improve our ability to distinguish between these scenarios. The Laser Interferometer Space Antenna, scheduled for launch in the 2030s, will detect gravitational waves at frequencies between those accessible to pulsar timing arrays and ground-based detectors like LIGO. This will allow us to track supermassive black hole binaries as they transition from the pulsar timing band through their final merger. The Square Kilometre Array, currently under construction in Australia and South Africa, will monitor hundreds of millisecond pulsars with unprecedented precision. This will improve the sensitivity of pulsar timing arrays by an order of magnitude, potentially allowing them to detect individual cosmic string events if they exist. As we push deeper into this mystery, we are not just identifying the source of the cosmic hum. We are probing fundamental questions about the nature of gravity, the evolution of galaxies, and the physics of the early universe. Each possibility opens different windows onto cosmic history, revealing different chapters of the universal story. The resolution of this deep cut between cosmic strings and black hole binaries will reshape our understanding of the cosmos. But even as we work to solve this puzzle, another mystery demands our attention, one that strikes at the very heart of cosmology itself: the rate at which the universe is expanding. The rate at which the universe is expanding should be one number. It is not. This simple fact has become one of the most pressing crises in modern cosmology, a contradiction so fundamental that it threatens to unravel our entire model of the cosmos. The expansion rate of the universe, known as the Hubble constant, tells us how fast galaxies are moving away from us based on their distance. It sets the scale for everything in cosmology, from the age of the universe to the distance to far-off galaxies. For decades, astronomers struggled to pin down its value, with measurements varying by factors of 2 or more. By the early 2000s, we thought we had finally solved this problem. We were wrong. Today, we have two extraordinarily precise measurements of the Hubble constant, and they disagree. One method looks at the early universe using the cosmic microwave background radiation to determine how fast space was expanding shortly after the Big Bang. The other examines the local universe, measuring distances to nearby galaxies to see how fast they are receding from us now. These two approaches should give the same answer. They do not. The early universe method relies on the cosmic microwave background, that faint afterglow of the Big Bang that fills all of space. This radiation carries within it a pattern of tiny temperature fluctuations, hot and cold spots that represent density variations in the infant universe. The size of these spots depends on several factors, including how fast the universe was expanding when the light was released about 380,000 years after the Big Bang. The Planck satellite, which mapped the cosmic microwave background with unprecedented precision, measured these spots and used them to calculate the expansion rate. After accounting for the universe's evolution from then to now, Planck determined that the Hubble constant should be 67.4 kilometers per second per megaparsec. This means that for every megaparsec, about 3.3 million light-years of distance, galaxies should be moving away from us 67.4 kilometers per second faster. The precision of this measurement is remarkable. The uncertainty is less than 1%, a triumph of modern observational cosmology. But this triumph has become a puzzle because the late universe tells a different story. The local measurement uses what astronomers call the cosmic distance ladder, a series of techniques that build upon each other to measure distances to ever more distant objects. The first rung involves parallax, the apparent shift in position of nearby stars as Earth orbits the Sun. This gives us distances to stars within a few thousand light years. The next rung uses variable stars called Cepheids. These stars pulsate with a period directly related to their intrinsic brightness. By measuring their pulsation period, we know how bright they truly are. Comparing this to how bright they appear tells us their distance. Henrietta Swan Leavitt discovered this relationship over a century ago, and it remains one of our most reliable cosmic yardsticks. Cepheids can be seen in galaxies millions of light years away, but to reach further, we need another rung. Type 1 A supernovae, the explosions of white dwarf stars, serve this purpose. These stellar explosions have nearly uniform peak brightness, making them excellent standard candles. By calibrating their brightness using galaxies with known Cepheid distances, we can use them to measure distances to galaxies billions of light years away. The SH0ES team, led by Adam Riess, who won the Nobel Prize for discovering the acceleration of the universe's expansion, has refined this distance ladder to extraordinary precision. They measure the Hubble constant to be 73.0 kilometers per second per megaparsec, with an uncertainty of just 1%. The difference between 67.4 and 73 might seem small, but given the precision of both measurements, it represents a 5 sigma discrepancy. In particle physics, 5 sigma is the gold standard for claiming a discovery. Here, it signals a crisis. Either one or both measurements have an unidentified systematic error, or our standard model of cosmology is incomplete. Astronomers have scrutinized both methods intensively, searching for overlooked sources of error. Perhaps the Cepheid calibration is flawed. Maybe dust in galaxies dim supernovae in unexpected ways. Could the cosmic microwave background analysis make incorrect assumptions about the early universe? So far, no convincing errors have been found. Independent measurements have only deepened the mystery. Gravitational lensing, where the gravity of galaxy clusters bends light from distant objects, provides another way to measure the Hubble constant. Some lensing studies favor the higher value, others the lower. The disagreement persists. Red giant stars offer yet another approach. These evolved stars have a maximum brightness set by fundamental physics, making them useful distance indicators. Recent measurements using red giants give values between the two extremes, around 69.8 kilometers per second per megaparsec. Rather than resolving the tension, this intermediate value raises new questions. Gravitational waves provide a completely independent method. When neutron stars or black holes merge, they emit both gravitational waves and light. The gravitational wave signal tells us the distance to the merger, while the light tells us the galaxy's redshift. Together, these give the Hubble constant. The first such measurement from a neutron star merger gave a value consistent with both extremes due to large If the discrepancy is real, it implies new physics beyond our standard model. Several possibilities have been proposed, each with profound implications. Dark energy might not be constant. Our standard model assumes dark energy behaves like Einstein's cosmological constant, maintaining the same density as the universe expands. But if dark energy changes over time, becoming stronger or weaker, it would affect the expansion history in ways that could reconcile the two measurements. Some models invoke scalar fields, similar to the field that may have driven cosmic inflation, that slowly evolve and change the dark energy density. Extra relativistic particles could exist in the early universe. Our standard model includes 3 types of neutrinos, nearly massless particles that rarely interact with matter. If there were additional particle species, perhaps sterile neutrinos that interact even less, they would contribute to the radiation density of the early universe. This would change the sound horizon in the cosmic microwave background, potentially bringing the early universe measurement into agreement with the late universe value. Dark matter might interact with itself or with dark energy. If dark matter particles can collide and scatter off each other, or if they interact with dark energy, it would affect structure formation and the expansion history. These interactions could be weak enough to have escaped detection so far, while still being strong enough to resolve the Hubble tension. The universe might not be perfectly uniform. Our standard model assumes the universe is homogeneous and isotropic on large scales, the same everywhere and in all directions. But if we live in a cosmic void, a region with below average density, it could affect local measurements of the expansion rate. The challenge is that such a void would need to be enormous, billions of light years across, and there is little independent evidence for such a structure. Modified gravity theories offer another avenue. Perhaps Einstein's general relativity, while extraordinarily successful, needs modification on cosmic scales. Some theories add extra dimensions. Others modify how gravity behaves at low accelerations. These modifications could alter the expansion history in ways that resolve the tension. Early dark energy presents an intriguing possibility. This hypothetical component would have existed only in the early universe, contributing about 10% of the total energy density around the time of recombination before disappearing. This extra energy would change the sound horizon in the cosmic microwave background without affecting the late universe, potentially reconciling the measurements. The implications extend beyond cosmology. The Hubble constant sets the age of the universe. With the Planck value, the universe is 13.8 billion years old. With the local value, it is only 12.5 billion years old. This difference matters for understanding stellar evolution, galaxy formation, and the timeline of cosmic history. The distance scale of the universe depends on the Hubble constant. A higher value means galaxies are closer than we thought, affecting our understanding of their properties. Dark energy's influence would be stronger, and the universe's fate might be different than predicted. New observations are rapidly accumulating. The James Webb Space Telescope is observing Cepheid variables and supernovae with unprecedented precision, checking for systematic errors in the distance ladder. The Dark Energy Survey and other projects are mapping millions of galaxies, providing new ways to measure the expansion rate. Future experiments promise even greater precision. The Vera Rubin Observatory will discover thousands of supernovae, dramatically expanding our sample. The Nancy Grace Roman Space Telescope will measure distances to unprecedented accuracy. The Euclid mission will map the three-dimensional distribution of galaxies across much of the sky. Pulsar timing arrays might contribute to solving this mystery. If they detect the gravitational wave background from supermassive black hole mergers, it will provide information about the galaxy merger rate, which depends on the expansion history. This could offer an independent constraint on the Hubble constant. The cosmic microwave background still has secrets to reveal. Ground-based experiments in Chile and the South Pole are mapping its polarization with increasing precision. These measurements could detect signatures of early dark energy or extra-relativistic species. As we grapple with this tension, we must remember that crisis often precedes breakthrough. The failure of classical physics to explain black body radiation led to quantum mechanics. The orbit of Mercury's disagreement with Newton's predictions led to general relativity. Perhaps the Hubble tension signals another revolution in our understanding of the cosmos. The universe is telling us something profound through this disagreement. Two precise measurements, each the culmination of decades of work, point to a gap in our knowledge. As we work to resolve this tension, we are uncovering new mysteries, including the puzzling absence of most of the normal matter that should fill the cosmic web. The puzzling absence of most of the normal matter that should fill the cosmic web represents one of astronomy's most vexing accounting problems. We call it the Missing Baryon problem, and it strikes at the heart of our understanding of cosmic structure. Baryons are the particles that make up everything we see around us. Protons and neutrons, the building blocks of atomic nuclei, are baryons. Every atom in your body, every star in the sky, every planet and moon and asteroid, all are made of baryonic matter. Yet, when astronomers add up all the baryons we can see in the universe today, we come up short. Very short. The early universe tells us exactly how many baryons should exist. Two independent methods give us this cosmic census with remarkable precision. The first comes from the cosmic microwave background, whose tiny fluctuations encode information about the baryon density in the young universe. The second derives from Big Bang nucleosynthesis, the process that created the first atomic nuclei minutes after the Big Bang. The abundance of deuterium, helium, and lithium depends sensitively on the baryon density during this epoch. Both methods agree that baryons should make up about 5% of the total energy density of the universe. Dark matter accounts for 27%, dark energy 68%, leaving 5% for normal matter. This might seem like a small fraction, but it represents an enormous amount of material, enough to make billions upon billions of galaxies. When we look at the universe today, we can account for only about half of these baryons. Stars contain about 7% of the expected total. Cold gas in galaxies adds another 7%. Hot gas in galaxy clusters, detected through its X-ray emission, contributes about 4%. The circumgalactic medium, the gas surrounding galaxies, holds perhaps another 5%. Adding it all up, we find only about half of the baryons that should exist. where are the rest? They are not truly missing, astronomers believe, but hidden in a form that has proven extraordinarily difficult to detect. Theory predicts they reside in the warm, hot intergalactic medium, often abbreviated as WHIM, a vast network of gas filaments stretching between galaxies. Computer simulations of cosmic structure formation paint a compelling picture of where these baryons should be. As the universe evolved, gravity pulled matter into a vast cosmic web, with galaxies forming at the densest nodes where filaments intersect. The filaments themselves, stretching millions of light years between galaxies, should contain gas heated to temperatures between 100,000 and 10 million degrees Kelvin. This temperature range creates a detection challenge. The gas is too hot to emit the spectral lines we use to study cool gas in galaxies, but too cool to produce the X-rays that reveal hot gas in galaxy clusters. It exists in a thermal sweet spot that makes it nearly invisible to traditional astronomical observations. The WHIM should be everywhere, forming the scaffolding of the cosmic web, but its low density makes it incredibly difficult to observe directly. The gas is about 1 atom per cubic meter, a density so low that a volume the size of Earth would contain less material than in a single breath of air. Yet integrated over the vast volumes between galaxies, it should contain enough baryons to solve our accounting problem. Several observational strategies have been deployed to find this hidden gas. X-ray absorption spectroscopy looks for the shadows cast by WHIM as light from distant quasars passes through it. When X-rays encounter highly ionized oxygen, nitrogen, or other heavy elements in the WHIM, they are absorbed at specific energies, creating absorption lines that reveal the gas's presence. The challenge is that these absorption lines are weak and require extremely bright background sources and sensitive X-ray telescopes to detect. Early observations with the Chandra X-ray Observatory and XMM Newton telescope found tantalizing hints of WHIM absorption, but the signals were often at the edge of detectability, making definitive claims difficult. Ultraviolet observations offer another window. The Hubble Space Telescope and the Far Ultraviolet Spectroscopic Explorer have detected absorption from 5 times ionized oxygen, a tracer of gas at a few 100,000 degrees. These observations have revealed warm gas around many galaxies, but whether this gas extends into the true intergalactic medium remains uncertain. The Sunya-Yves-Zeldovich effect provides a different approach. When cosmic microwave background photons pass through hot gas, they gain energy through scattering off high-energy electrons. This creates a distortion in the cosmic microwave background spectrum that can reveal the presence of hot gas. While this effect has been used successfully to study galaxy clusters, detecting the more diffuse WHIM requires greater sensitivity than current instruments provide. A breakthrough came from an unexpected source: fast radio bursts. These mysterious flashes of radio emission, lasting just milliseconds, appear to come from distant galaxies. As the radio waves travel through space, they are dispersed by free electrons along the line of sight. The amount of dispersion tells us the total electron content between us and the burst source. When astronomers compared the dispersion measure of fast radio bursts to the number of galaxies along the line of sight, they found more electrons than could be accounted for by galaxies alone. The excess matches predictions for the double UHIM, providing independent evidence that the missing baryons are indeed hiding in intergalactic space. Recent observations have begun to map the double UHIM more directly. The European Space Agency's XMM Newton telescope conducted a deep observation of a bright blazar, a type of active galaxy with a jet pointed toward Earth. The 16-day observation revealed absorption from highly ionized oxygen at the redshift of a galaxy group along the line of sight. The absorption strength and temperature implied a filament containing about 10 billion solar masses of hot gas, consistent with simulations of the WIM. Stacking analyses have provided statistical detection of the WIM. By combining observations of many quasar sightlines that pass near known galaxy pairs, astronomers can boost the signal-to-noise ratio enough to detect weak absorption. These studies find that galaxy pairs are indeed connected by filaments of hot gas, with properties matching theoretical predictions. The cosmic web is not uniform. Simulations show that filament properties depend on their environment and evolution history. Filaments feeding massive galaxy clusters are shock-heated to higher temperatures and contain more metals from enrichment by galactic winds. Filaments in lower density regions remain cooler and more pristine. This diversity complicates observational strategies, but also provides opportunities to study different phases of the double UHIM. Metal enrichment offers crucial clues about the double UHIM's history. Heavy elements like oxygen and iron are produced in stars and ejected into space through stellar winds and supernova. The presence of these metals in the double UHIM tells us that some of this gas has been processed through galaxies before being expelled into intergalactic space. The metallicity, typically about 1/10 of solar values, suggests a complex history of cycling between galaxies and the intergalactic medium. Galactic feedback plays a central role in populating the double UHIM. Supernovae and active galactic nuclei drive powerful winds that expel gas from galaxies. This gas, heated and enriched with metals, joins the cosmic web filaments. Some of it may eventually fall back onto galaxies, fueling future star formation in a grand cosmic recycling process. The missing baryon problem connects intimately with galaxy evolution. Galaxies are remarkably inefficient at converting baryons into stars. A typical galaxy has turned only about 20% of its available baryons into stars. The rest has been ejected or prevented from cooling and forming stars. Understanding where these baryons go and how they interact with galaxies is crucial for a complete picture of galaxy formation. Future observations promise to revolutionize our understanding of the double UHIM. The Athena X-ray Observatory, planned for launch in the 2030s, will have unprecedented sensitivity to absorption lines from hot gas. Its high-resolution spectrometer will detect WHIM filaments that are invisible to current telescopes, potentially providing a complete census of the missing baryons. The Square Kilometer Array and other next-generation radio telescopes will detect thousands of fast radio bursts, each providing a probe of the electron content along its line of sight. By mapping the dispersion measures of bursts across the sky, astronomers will create a three-dimensional map of the baryon distribution in the universe. The Line Emission Mapper, a proposed space mission, would map emission from the WHIM directly rather than relying on absorption against background sources. This would reveal the structure of the cosmic web in unprecedented detail, showing how filaments connect galaxies and feed galaxy clusters. Ground-based optical telescopes are also contributing. The Keck Observatory and Very Large Telescope have detected emission from cosmic web filaments in deep observations of galaxy cluster outskirts. These observations reveal gas streams feeding clusters, providing direct images of the cosmic web in action. The interplay between dark matter and baryons shapes the cosmic web. Dark matter forms the gravitational backbone, creating potential wells that guide baryon flows. But baryons are not passive tracers. Their pressure, cooling, and feedback processes affect how structures form and evolve. Understanding this interplay requires sophisticated simulations that include both dark matter dynamics and baryon physics. Magnetohydrodynamic simulations now include magnetic fields, cosmic rays, and detailed models of stellar and black hole feedback. These simulations make specific predictions for WHIM properties that can be tested with observations. The agreement between simulations and observations has improved dramatically, building confidence that we understand the basic picture while revealing areas where our models need refinement. The missing baryon problem also relates to cosmological parameters. The baryon fraction in galaxy clusters is lower than the cosmic average, implying that some baryons have been expelled or never accreted. This baryon deficit depends on cluster mass and redshift, providing clues about the heating and feedback processes that shape the baryon distribution. As we close in on a complete baryon census, new questions emerge. How do baryons flow through the cosmic web? What fraction cycles through galaxies multiple times? How does the double UHIM affect galaxy evolution? These questions connect the missing baryon problem to broader issues in cosmology. The cosmic web represents the largest structures in the universe, spanning hundreds of millions of light years. Yet, it is built from individual atoms, particles so small that 10 million could fit across the width of a human hair. This vast range of scales, from subatomic to cosmic, challenges our observational techniques and theoretical models. Even more challenging are particles that might not behave like particles at all, but rather as waves on cosmic scales.